Finding a standard normal probabilities using a z-table. Suppose that we have a random variable that follows a z-distribution. I'm going to call the random variable z. Since it follows a z-distribution, it means that it follows a normal distribution with an average of 0 and a standard deviation of 1. Suppose that we want to find a probability for z. For example, the probability that z is less than 12%. How can we find this probability? Well, this is a continuous random variable. So if you remember for the discrete random variable, what we had to do if we wanted to find the probability that a random variable less than or greater than something, we had to add up for all the values that the random variable would take. But this is a continuous random variable. That means that it can actually take any values, infinite values. For example, there are infinite numbers between 1 and 2, and between 0.2 and 0.3. There are infinite numbers. So we can just add up. What is the equivalent of adding up for continuous random variables? But if you recall from calculus, that is integral. Remember integral? All right, so that is pretty much what we have to do here. So if you want to find the probability that z is less than 12%, we have to find the shaded area here, which would be the equivalent of finding the probability, the integral. So this would be the area here, the blue area, dark blue area here. That would be equal to this probability. But how can we find this area? Also, if you remember from calculus again, what you need to do is to have this function, the function of this red curve, which is the normal distribution, the z distribution, f of x. You need to have this and then find the integral of f of x from negative infinity to this value, 12%. And that's going to be the blue shaded area. Okay, so let's go back and see the formula, the f of x, the probability density function of a normal distribution. This is the function. It's a pretty complex function. So what you need to do if you wanted to solve it mathematically, we would have to replace sigma and mu here. Mu is 0, so we have to replace this mu here with 0. That would be 0. And sigma is 1. So this would be 1. Also, this one would be 1. Okay. After we do that, we can find the probability. But that's not an easy task to do. It sounds and look difficult and time consuming and tedious. So, and this is especially even true now that we have computers and calculators, advanced computers and softwares. But think about like 100 years ago or more. How could people find such a probability using this method or function? Well, this is what we want to talk now. It's called z-table. In the past, they used a table called z-table that you see here. So z-table has all the probabilities for different values that z can take. On the first row here, you see the first decimal of the value that z can take. Z means this value here, the small z. So we have a big capital Z here, which is the random variable, and we have a small z here, which is the value that the random variable can take. So the first row shows the first decimal, and the columns, the next columns, you see, it covers the second decimals. So for example, we are looking for 12% here. Z here is 12%. 12% has 0.1, so 0.1 is here, as you see here. This is 0.1, and also 0.02 as the second decimal. So the intersection of these would be our solution. So that's 0.5478. That's the probability. So this probability is equal to 0.5478. That's the probability. So instead of going through all these complicated formula and computation using this very complex probability density function and using an integral, we can actually use this table to do that. Well, right now we don't need to do this because we have computers and we can just plug in the numbers, and I'm going to show you how to can do that in Excel. But back then, back in the time, they used this table, which is called Z table. Let's do another example. Suppose we wanted to find the probability that Z is less than 46%. Okay, so what we need to do, we need to find the first decimal here in the first row, so that would be fourth decimal, 0.4, and the second decimal, which is 6, we have to find it in the column, and the intercept of these two, the intersect would be here and here, so that would be our solution, which is 0.6772. So this probability is equal to 0.6772. We will see more examples of this to learn how to master this method. Computing general normal probabilities. So we learn how to use the Z table to find the probabilities for Z distribution. But what does have to do with a general normal distribution? So for example, suppose that we have a normal distribution, X would follow a normal distribution with average of mu. I'm going to go general here, and a standard deviation of sigma. So mu and sigma can be any values. We are talking about general example here. And suppose that we want to find the probability that X is less than any value, a small x. So here I show the random variable by a capital X, and I show the value that it takes by a small x. So a small x here is the value that it takes. If we use y, the capital Y would be the random variable, and a small y would be the value. If we use z, the capital Z would be the random variable, and a small z would be the value. So we want to find this probability. How can we solve this problem? With one way actually is to use the probability density function and the integral, because this is a cumulative probability, the probability that X is less than a small x. So if I actually plot the probability distribution of normal here we have the mu here, and what we are looking for is, suppose X is here, this is X, then what we have to do is we have to find all this probability, which means the shaded area from the negative infinity, from negative infinity to a small value x right here. And the shaded area in green, colored in green, that would be the probability. But how can we find that, the shaded area here? Well, this is actually equal to the integral from negative infinity to value x, f of x, which is the probability density function of normal distribution, d of x. So if we solve this integral, that would give us the probability that x is less than a small x. And this is that usually it's work. This is how in Excel and any other software, statistics software, this is how it works. But I want to show you how in the past, back in the time when they didn't have advanced calculator or computers or software, they how did they solve this problem? Well, actually, they use the z-distribution table. The fact is actually we can convert this probability that x is less than x, into a z-distribution probability. So this would be equal to the probability that z is actually the follows the z-distribution or a standard z-distribution less than z-score of x. And if we find this probability, that's equal to the probability that x is less than x. How can we find the z-score of x? The z-score of x is equal to x, the value x, minus the average mu, which comes from here, of course, divided by its standard deviation, which is sigma. And sigma comes from here. Okay? If we find the value of z of x and the probability that z is less than the z value of x, that would be equal to the probability that x is less than x. So this would all make more sense when we do an example. So let's go ahead and do an example for this. Suppose that x is a random variable that follows a normal distribution with an average of 5 and a standard deviation of 2. So always the first value in normal distribution is the average mu, and the second value is the standard deviation. This is always true for normal distribution. All right, so we have this random variable, and we want to find a probability, for example, that x, random variable x, is less than 7. So we can actually use Excel, and we can use actually the integral to solve this. So this would be equal to the integral of from negative infinity to 7 f of x d of x, and if we solve this, it's going to be equal to the probability, or we can actually convert this to a z distribution and find it using the z table. So let's now do that. So this would be equal to the probability that z is less than z-score of 7. What is the z-score of 7? Z-score of 7 is equal to 7 minus the average mu. Mu here is 5, comes from here, 5, divided by standard deviation 2, which comes from here, of course, 2. So if we solve this, this is equal to 7 minus 5, that's 2, divided by 2, which is equal to 1. So the probability that x is less than 7 is equal to probability that z is less than 1. And if we find this, the probability that z is less than 1 in the z table, that's going to be equal to the probability that x is less than 7. And we're going to do that in just a second. Before that, let's move on with another example. Suppose that you also want to find the probability that x is less than 4.3. So again, we can convert this to a z distribution. So that would be equal to the probability that z is less than the z-score of 4.3. And let's find the z-score of 4.3. Z-score of 4.3 would be equal to 4.3 minus the average, which is 5 here, 5, divided by standard deviation 2. And if you solve this, it's equal to negative 0.35. So that would be the z-score of 4.3. So if you find the probability that z is less than negative 0.35, that would be equal to the probability that x is less than 4.3. And we're going to look at the z-table to find this probability. As you see here, we have the z-values, the first decimals on the column here, and then we have the second decimals from 0, 0.0, 0.02 up to 0.09 here. And it starts from negative 309 and it goes to negative 309 here, and then goes to positive 309. It doesn't have for values beyond that because the values are really going to be small differences as you look here. All right, so let's see also for positive. The next page shows for the positive starting from 0 and then goes to positive 309, as you see here, positive 39. So it says for value z greater than 3.09, the areas are 1 to 4 decimals places. That means that to 4 decimals, the value is the same. So if you're looking for more than, if you don't look for more than 4 decimals, then you shouldn't care about the more than 309. You can just approximate it with 309. For example, if you were looking for 5, then the value would be to 4 decimals, it would be 10.000. So that's the same would apply for negative 309. So if you had, for example, wanted to find the probability that z is less than negative 6, for example, negative 6 is less than 3.09, but to 4 decimals it would be 0.0000. So that's a good estimation. All right, so now let's actually solve for the problem that we have. We want to find the probability that x is less than 7. Okay, x is less than 7, that means that that's equivalent to z less than 1. Z less than 1. Okay, so let's find that. We go to positive first. We have 1 here, and 1 is 1.000, so that would be 0.8413. The next one that we want to find is we want to find the probability that x is less than 4.3. 4.3 is equal to finding the z is less than negative 0.35. Negative 0.35. So we have to go to negative values, the first page. Negative 0.35. The columns, the first one is for 0, 0.1, 0.02, 0.03, 0.04, and 5. So we have to look for this column and for 3, 5. So that would be 3, 5, which is 362. 3.3632. All right, so we found the probability using the z-table, and that would be the probability that x is less than 7. That's the probability that z is less than 1, and we found that to be 0.8413 using the table. The probability that x is less than 4.3 is equal to the probability that z is less than negative 0.35, and using the table we found that that's equal to 0.3632. Okay, now let's see another example. Suppose that we want to find the probability that x is equal to 6. Well, it might be surprising to you, but this is actually equal to 0. And for any value of x, the probability that random variable x, a normal distribution, or any continuous random variable is less than is actually equal to value x is 0. Why is that? Well, I'm going to tell you how it is in terms of normal distribution. So in terms of normal distribution, if you look at the probability distribution function, this is mu here, for example. Suppose that this is x that you want to find the probability for. So the probability that x is equal to 6 here, suppose this is 6 here, suppose this is 6. So the probability that x is equal to 6 is equivalent to a rectangular here with an area of 0. So the length of this rectangle is from 0.6 to 0.6, which is 0. Right? So the length of this rectangle is 0, and the height of it is whatever it is f of 6 actually. It's f of 6. So the area of this rectangle, which is equal to the probability of x equal to 6, is 0. Okay. For any other value, the probability that x equal to 9, that's also 0. The probability that x is equal to negative 7, that's also 0. So for any value of x, no matter what it is, the probability that is exactly equal to that is 0. And to help you understand this more, suppose that we have infinite number of students in class. That's what we have in a continuous random variable. The random variable can take, a continuous random variable can take infinite numbers. So if we have infinite numbers in class and I want to take u specifically, what would be the probability? It would be 1 over the number of students in the class, which will be 1 over infinity. 1 over infinity, and 1 over infinity would be 0. There will be 0 chance. Okay, so the for a random variable that is continuous, no matter it's normal distribution or any other distribution that we're going to learn in the future, if it's continuous, the probability that x takes is specifically exactly one value would be 0. Would be 0, right? Okay, so let's see another example. Probability that x is less than or equal to 7. So this is different from this one that we have here. In the first one, we had strictly less than 7. That means that not including 7, not equal to 7, just less than 7. In 4, we have the probability that x is less than 7 or equal to 7. So that includes 7. Well, try to see what do you think this is equal to? Try to think about it. Well, actually, we can write this into the probability that x, so this is equal to the probability that x is less than 7 plus the probability that x is equal to 7, right? This is what it means. The probability that x is less than or equal to 7, this is equal to these two, right? And we know that the first one is number 7 here, which is 0.8413. The second one, however, this one, we learned that it is 0, equal to 0, from 0.3. We learned that this is equal to 0. So basically, this means that the probability that x is less than or equal to 7 is equal to the probability that x is less than 7 strictly, and that would be equal to 0.8413 that we have here. So these two would be equal. So number 4 would be equal to number 1. These two are equal. How about number 5, the probability that x is less than 4.3? Well, you can look at number 4 and conclude that for number 5 would be the same. It would be equal to, we can rewrite it as the probability that the x is strictly less than 4.3 plus the probability that x is equal to 4.3, which would be the probability that we had in number 2, which is 3.3632 plus 0, which we got it from here, from number 3. And that would be equal to 0.3632. Let's now see how the normal distribution function works in Excel. Excel provides a function for a normal distribution, both for general normal distribution and for a standardized normal distribution. These are the functions. Suppose that x is a random variable that follows a normal distribution, and the function to find the probability that x is less than a small value x is norm.dist, and then we have 4 parameters: x, comma, mu, the average, comma, standard deviation, comma, 1. You put 1 because we are looking for a cumulative here, because we have less than, right? So that would be cumulative, and it would be equal to the area that you see here, the shaded blue area here. Excel also has a function for a standard normal distribution, as you see here in the second function. This is the probability that z, the standard normal distribution, is less than a small z, is equal to norm.s, stands for standardized, norm.s.dist, and you just put z here. And that's going to give you the probability distribution, the probability, or you can also work with the parameter could have, in some Excel function, you could have to add another one for cumulative or not here. So let's actually solve the problem here. So suppose that we want to find the probability that z is less than 0.12. So using Excel function, the second function here, so that would be norm.s.dist, and then z, which is 0.12, and that would be equal to 0.5478, and that's equal to the shaded area of the blue area here. All right, so now let's actually see this in Excel. Let's now use Excel to find the probability here, normal distribution. So suppose that we have the same problem, that x is a random variable that follows a normal distribution with an average of 5 and a standard deviation of 2. Now we want to find, for example, probability that x is less than 7. So, which is our previous example. So this would be, we're going to put norm and then .dist, norm.dist. The first parameter here is x. So x here is 7, then comma, the second one is mean, the expected value, which is 5 here. 5, comma, the next one is the standard deviation, which is 2 here, comma, and the next one we have to put true because we are looking for cumulative. Okay, and we hit enter and we get 0.8413, which is similar to what we found before. Let's do the other example here. The probability that x is less than 4.3. So that is equal to the probability. We're going to use the norm function. So that would be norm.dist. The first one is x, which is 4.3 here, comma, the next one is mean, the average, which is 5, comma, the next one is standard deviation, which is 2, comma, and the next one is going to be true or 1, which is for the cumulative. And we close the parentheses and hit enter, and we get 0.3631. All right, and if you want to find, for example, the probability that for a z distribution, that z is less than 0.12, for example. So this would be equal to, the function for that is equal to norm dot s, stand for standard distribution, and dist. So norm dot dist dot s dot dist. The first parameter is z, which is here 0.12. So here we don't have mu, the mean and the standard deviation, because the mean and standard deviation of z distribution is 0 and 1. So the function already knows that, and we are looking for a cumulative. So we put true or 1, and we hit enter, and we get the probability. So I'm going to copy the function here for you. So we get here, and this is the function. And for this one, the same, I'm going to copy it here. So now you have it here. And this is for the z distribution. I'm going to copy it here. So this is how it works in Excel. For the normal distribution, general normal distribution is norm.dist. For the z distribution is norm.s.dist.